use mathematical induction to prove that the sum from r equals 1 to n of r times r plus 2 is equal to n over 6 times n plus 1 times 2n plus 7. So let's start with our first step. Step 1 is when n is equal to 1, because that's the smallest that n can be. The left-hand side is the sum from r equals 1 up to 1 of r times r plus 2. We substitute r equals 1 in to get 1 times 1 plus 2, which is equal to 3. On the right-hand side, we have 1 over 6 times 1 plus 1 times 2 times 1 plus 7, which is equal to 1/6 times 2 times 2 plus 7 is 9. That's 1/6 of 18. 1/6 of 18 is 3. The left-hand side and the right-hand side are equal when n is equal to 1. So therefore, the statement holds for n equals 1. The base case is true. Step 2 is our assumption, n is equal to k. We're going to assume that the sum of r equals 1 up to k of r plus 2 is equal to k over 6, k plus 1, 2k plus 7. Now we move on to step 3. Step 3 is our inductive step, where n is equal to k plus 1. What we want to show is that the sum from r equals 1 up to k plus 1 of r plus 2 is equal to k plus 1 over 6. K plus 1 is k plus 2. And 2k plus 7, well, replacing the k with k plus 1 is 2k plus 1 plus 7, but that simplifies to 2k plus 2 plus 7, which is 2k plus 9. So I'm just going to write that down as 2k plus 9 in the simplified form. Start with the left-hand side. We always follow the same process with these sigma ones, which is we start by splitting up that sigma notation so that we count up to k, and then we add on to that this thing evaluated at k plus 1. So when r is k plus 1, we get k plus 1 times k plus 1 plus 2, which is k plus 3. We substitute k plus 1 in here, k plus 1 plus 2 gives me k plus 3. Now we make the substitution using our assumption step, which means this whole thing here is going to be k over 6 times k plus 1 times 2k plus 7, and then plus k plus 1, k plus 3. Now, if you prefer at this stage, you could expand this and you could expand this and show that those two things are the same. I'm going to go through the method I showed in the last video, which is factorizing this expression to get there a little bit more quickly, although it is a little bit more difficult. So the first thing I'm going to realize is that these two expressions have a k plus 1 in common, so I can factorize out that k plus 1. But I'm also going to realize that in the what I want to show, I have a k plus 1 over 6. So actually, I'm going to factorize out k plus 1 over 6, because I know that's what I want to end up with at the end. What do I need to multiply k plus 1 over 6 by to get this green expression? Well, I need a k, and a 2k plus 7. What do I need to multiply k plus 1 over 6 by to get this red expression? Well, k plus 3, but also because I have the divide by 6 here, I need to multiply by 6 to counterbalance that. That now gives me k plus 1 over 6. Expanding this out now, I get 2k squared plus 7k here, plus 6k, so that's plus 13k, and then plus 6 times 3 is 18, which is k plus 1 over 6 times, factorizing this, I'm going to have one bracket with 2k and one bracket with k. Multiply to make 18 means I'm probably dealing with 2 and 9, and they need to add to make 13. Well, 2 times 2 plus 9 would give me the 13, so I factorize it like that. And then I notice that this is actually exactly what I wanted to show. That is indeed the right-hand side. So I've shown what I wanted to show is true. Finally, I have step 4, which I must always have on any of my proof by inductions. And step 4, as always, states that a mathematical induction statement is true for n equals 1. If it holds for n equals k, it also holds for n equals k plus 1, so it must be true for all numbers.